So let's spend a little more time exploring this idea of the reaction quotient. We've seen so far that if I take a product of the number of molecules or moles of each species raised to their stoichiometric coefficient, that's equal to, when I'm at equilibrium, the product of the partition functions raised to their stoichiometric coefficients. On the the right side, this product of partition functions is something we call the equilibrium constant. On the right side, the product of the number of molecules of each species, that's called the reaction quotient. And it's the one on the left, this reaction quotient that changes as the reaction proceeds forward or backward. So the reaction moves forward or backward until the reaction quotient becomes equal to the equilibrium constant. The equilibrium constant is just a constant. The reaction quotient can change as the reaction proceeds. Certainly, it's possible to figure out the extent of reaction that will let us reach equilibrium. That's one way that we use this expression. But the other thing the reaction quotient is good for is telling us simply in what direction a reaction is likely to go, whether we think it should go forwards or backwards. So for example, consider just an arbitrary reaction where A plus B and some other reactants might proceed and form C plus D and some other products. The reaction quotient in this case, products over reactants, is molecules of C times D and any other products divided by molecules of A and B and any other reactants. The reaction quotient is the amount of each species present at any given moment. So if the reaction has already proceeded to some degree, the number of molecules of the product is the initial amount plus the extent of reaction. The amount of each reactant is the initial amount that was present minus the extent of reaction. So when the reaction goes forward, when squiggle is a positive number, I've gained products and I've lost reactants. But what that means is when the reaction does proceed forward, if squiggle is a positive number, if it's getting larger, as squiggle gets larger, because squiggle appears with a plus sign in the numerator is getting larger. In the denominator, squiggle shows up with a minus sign, so the denominator is getting smaller. So as the reaction proceeds forward, the numerator is getting bigger, the denominator is getting smaller. That means the reaction quotient is getting larger. The more the reaction proceeds, the larger Q gets, the larger the reaction quotient gets. If the reaction goes all the way to completion, if I consume one of the reactants completely, whichever one is the limiting reagent, if I consume it completely so there's none of it left, one of the terms in the denominator will be a zero, and then the largest Q can be is it will reach infinity when I divide by zero. So when the reaction goes to completion, the reaction quotient becomes infinite. On the other hand, flip the signs of each of those statements. If the reaction proceeds backwards so that squiggle is getting smaller, either squiggle is a negative number or if I've consumed products to make reactants, when that happens, if squiggle is a negative number, then squiggle is negative, so the numerator is getting smaller. Subtract that negative number, the numbers in the denominator are getting larger. So the smaller numerator over a larger denominator means that Q is getting smaller. So when the reaction proceeds backwards, the reaction quotient decreases, and the smallest that can become is zero if I've completely consumed one of the products, so there's no more of it left. The number of moles or molecules of that product reaches zero, and the zero in the numerator means the reaction quotient can't get any smaller than zero when the reaction goes completely in reverse. So those statements lead us to the following conclusions. If Q happens at any given moment to be less than the equilibrium constant, we know Q is going to change and become equal to the equilibrium constant to reach equilibrium. So the way in which that happens, the way Q gets larger, is for the reaction to go forwards. Remember, Q gets larger when the reaction goes forwards. So when Q is less than the K, the reaction will proceed forwards in order to reach equilibrium. If Q is greater than K, it's already too large, then the reaction has to proceed backwards in order to reach equilibrium, because when the reaction proceeds backwards, that'll decrease the value of Q. And either of those things will happen, either proceeding forward or proceeding backward, until the point when Q equals K. And when the reaction quotient is equal to the equilibrium constant, then we know the reaction is at equilibrium and the reaction doesn't proceed any further in either direction. So what that means is if we know how much of each species is present, in this example, let's just say we have 0.01 moles of H2, 0.05 moles of Br2, and a mole of HBr in some reaction vessel at a temperature where we know the reaction coefficient, the equilibrium constant is 1800. In order to predict whether we're going to consume H2 and Br2 or whether we're going to consume HBr, we just calculate the reaction quotient, molecules of HBr squared over molecules of H2 times molecules of Br2. So a mole of HBr squared over 0.01 moles and 0.05 moles in the denominator. Those numbers work out to 2,000 for this simple example. The important thing is that number, that reaction quotient that we've gotten, is larger than K, larger than 1800. So we know from that statement that this reaction is going to proceed in reverse. H2 and Br2 are going to be produced, and HBr is going to be consumed in order to reach equilibrium. And if we care to, we can figure out exactly how much will be consumed by figuring out the exact value of the extent of reaction that will let us reach equilibrium. But as a first guess, it's pretty simple just to check whether the reaction is going to proceed forwards or backwards.